Good morning. Okay, yeah. So today we'll discuss about Laplacian matrices. So before defining the Laplacian matrix, we'll discuss about incidence matrix. Okay, it's also called a signed incidence matrix. You can think of. So given a graph G with a vertex at V and edge at E, just give a labeling to them. Let V12 Bn be the vertices and E12 Em be the edges. Okay. So given a graph, I can associate something called incidence matrix. Is denoted by Q. So this is an n by m matrix. Okay, so this is an n by m matrix. The rows are indexed by the vertices. Okay, so V1, V2 to Vn, and the columns are indexed by the edges. Okay, this is your matrix. The definition is Qij is, so you look at the edge. Okay, so before that, before defining it, so we are working with a simple graph, simple undirected graph. First give a orientation to all the edges. Okay, fix the orientation to all the edges. So after giving the orientation, if you take an edge, every edge will have a starting point and the ending point. Okay, a starting vertex or an end vertex. For an example, so if you take this graph, this is V1, V2, V3, V4. Let me give name to the edges E1, E2, E3, E4, E5. So this is a graph given to us. So for defining the incidence matrix, first we have to fix an orientation. By orientation I mean give direction to all the edges. Okay. After giving the direction, just fix it. Okay, we will define the incidence matrix for this orientation. If we change the orientation, the incidence matrix will change. Okay, the idea is this: you look at the column corresponding to the edge E1. Okay, so you put a -1 where the edge starts. Okay, so it starts at V1. So keep a 1 in the V1th place. Where it ends, keep a -1 there. Okay, -1 here. The rest of the places keep 0. Okay. Similarly for all other edges, we do this thing. E2, E3, E4, E5. So E2 starts at V2. So keep a 1 here. It ends at V3. So -1, 0, 0. What about E3? 0, 0, -1, 1. For E4, 0, 1, 0, -1. For E5, 1, 0, 0, -1. Okay. So we will define the Laplacian using this incidence matrix. So one reason is this definition of Laplacian using incidence. This extends for higher dimensional hypergraphs and other structures also. Okay. So how to write this? So ijth entry of the matrix Q is equal to 1 if the edge Ej starts at the vertex Vi. This is -1 if the edge Ej ends or terminates at Vi, 0 otherwise. Okay. So some simple observations we can do. What about the column sums of this matrix? The column sums are always equal to 0. So because the columns are always equal to 0, that means that if you take the vector E of appropriate size, E means all ones vector, that will be in the left null space of this matrix Q. Okay, E into Q is equal to 0 you will get. And one more thing, how many non-zero entries will be there in the rows? Degree of that vertex. If I fix the ith row, in the number of non-zero entries in the ith row gives you the degree of the vertex Vi. Okay. Now, if G is a connected graph, okay, so we already observed that this all ones vector is in the left null space of this matrix Q. Okay, so this is an n by m matrix. So rank cannot be more than n minus 1, because already we observed that the all ones vector in the left null space, the rank cannot be, rank should be less than or equal to n minus 1. So if we are working with a connected graph, then the rank of the instance matrix is exactly equal to n minus 1. Okay, so we'll prove that first. If G is a connected graph on n vertices, then rank of the incidence matrix is equal to n minus 1. Okay. So what's the proof? So we will use the left null space argument. So if I take any arbitrary vector, okay, so first we will start with the all ones observation. Let E denotes the all ones vector. Okay, which is in, call this is in Rn. Then E into Q, or E transpose into Q, this is equal to 0. Okay, so this tells us that rank of Q of G is at most n minus 1. Okay, now we will take some arbitrary vector in the left null space of Q, and we will show that that should be multiple of this all ones vector. If I can show that, then I am done.
So E is a column vector.
E is the column. So this is an 1 by n transpose I will take. Okay, yeah, thanks. So now let us take some arbitrary vector x in Rn such that x transpose Q is equal to 0. Okay. So the entries of x are given by x1, x2 up to xn. Okay. So if you take the vector x and if you multiply that with the first column of Q, what you will get? If you take this vector, if you multiply with the first column of Q, what are you going to get? What are the entries of the first column? The entries of the first column are 1 minus 1 or 0. Okay, so you are going to get exactly two non-zero entries in the first column. One is 1, the other one is minus 1. 1 corresponds to the vertex where the edge E1 starts, and minus 1 corresponds to the vertex where the edge E1 ends. Okay, so what I will get? So if E1 is the edge Ij, then Xi minus Xj, this is equal to 0. Okay. In general, if two vertices, okay, Ij used, let's say I1 and I2 are adjacent, then the component of the vector which I have taken from the null space of left null space of Q, they should have same entry. Okay, whenever you have an edge between the vertices I1 and I2, look at the column corresponding to that edge connecting them. Okay, that column contains 1, 1, 1 minus 1, rest of them are 0. So the non-zero entries corresponds to the xi and xj. So xi minus xj equal to 0, hence you are getting xi1 equal to xi2. Now we didn't use the fact that the graph is connected so far. Now if you use the fact graph G is connected, then what do you get? If I take two arbitrary vertices, between any two vertices of the connected graph, you have a path So along that path we are going to get all the terms of the vector x are constant, same. Okay, that shows that x should be a multiple of this all ones vector. Okay, since G is connected between any two vertices of G, we have a path connecting them, and along that path or the value of xi on the vertices in the path the values of all xi's on the vertices in that path are the same, are equal. Okay, that is x is just some constant multiple of E. Okay, so this shows that if G is a connected graph, then rank of the incidence matrix is n minus 1. Okay. So in fact something more can be said. If it is a graph on n vertices, if it has k components, okay, so maybe you can use the same argument to show that if G is a graph on n vertices with the k components, then rank of Q of G is n minus k. Okay, how to prove this? Is to use the block matrix argument. If G1 to Gk are the components of G, then what is Q of G? You can order the vertices of the graph and the edges of the graph in such a way that you keep all the vertices and the edges in the first block of the rows and first block of the columns. Okay, so it will be a diagonal matrix. So this is Q of G1 0 0 0, Q of G2 0. Now for each of the components you can apply the result which we put here. So that is going to give you, this implies rank of Q of G is equal to n minus k. In fact, the converse is also true. If rank of Q of G is equal to n minus 1, then G should be connected. How to see that? Just think proof by contradiction, you will get the answer. How to see that? If rank of Q of G is equal to n minus 1, then the graph should be connected. Okay, I'm saying think of proof by contradiction. Suppose G is not connected, then you can decompose the graph into, let's say, G1, G2, such that between G1 and G2 there is no edge. Now then Q of G can be partitioned into Q of G1 0 0, Q of G2. Okay. Now can you give me two linearly independent eigenvectors, left eigenvectors for this one? Okay, corresponding to G1 block, keep all ones and rest of them 0. Okay, and then the second eigenvector is, first keep zeros in the components corresponding to G1. In the components corresponding to G2, keep all ones. That's going to give you two linearly independent eigenvectors. That contradicts the rank.
Also follows from this one. If the rank is n minus 1 and you know rank is n minus k, then k has to be 1. It's the same.
Can you repeat?
So if the rank, because you're trying to prove the converse, if the rank is n minus 1,
yes,
you already know that the rank is n minus the number of components.
Yes, yes, yeah, that's also, yes. Okay, good. Is it okay? So now, maybe with this we will define the notion of Laplacian. So Laplacian is okay. So the same setup. G is a simple graph. So the Laplacian is again an n by n matrix. It is defined in this way. The ijth entry of the matrix is, keep the degree of that vertex in the diagonal. If I equal to j, you keep a minus 1. If I is not equal to j and I is adjacent to j, 0 otherwise. Okay, so we have seen about adjacency matrices. This Laplacian also can be equivalently defined in this way. The same, I'm just rewriting. This is d of g minus a of g. The d of g is the diagonal matrix whose diagonal entries are degrees of the corresponding vertices, and the a of g is the adjacency matrix. Adjacency matrix. Okay. So the first result I'm going to prove is kind of easy to see. For any graph G, the Laplacian of G is given by Q of G into QG transpose. Right? It's an n by n matrix here. So again, I will show only for one row or one column. Then rest of the things you can prove by your own. Okay. So statement clear? Okay. So let us look at some entry. First we'll start with some diagonal entry. Ith entry, how do you get the ith entry? The ith entry of the Laplacian take the ith row of Q of G and take the ith column. Okay. So what are the non-zero entries in the ith row? Everything is either plus 1 or minus 1. So how many non-zero entries are there? You will get degree of that vertex. Okay. And you are going to take the dot product with the transpose of the same vector. Okay. Hence you are going to get the degree of that vertex. Okay. What about the off diagonal entry? For I not equal to j, the ijth entry is so I is different from j. Okay. So if I had to get a non-zero entry, non-zero term, I'm taking the product of two vectors. Okay. So if the places of ones and minus ones in both the non-zero vectors, if they are disjoint, then I'm going to get 0. Okay. I will get non-zero entry only when there is a overlapping in the non-zero places. When you get a overlapping in this orientation, so we are fixing, whenever I'm talking about Q of G, I'm having a orientation there. Okay, so in that orientation, that edge EI, not the edge EJ, incident or starts at the vertex I or ends at the vertex I. Okay, so if it starts at the vertex I, then I'm going to get 1 in the common non-zero place. If it ends at that vertex, then I'm going to get minus 1 in the Yeah, so sorry, wait, what I'm saying. So let us write down that, okay. So in the ith row, I'm going to get the row corresponding to the vertex. That vertex consists of some 1, 0, minus 1 and so on. The column corresponding to Ej, this I'm going to get 1, 1 and 1 minus 1. Okay, rest of the entries are 0. Yes.
Actually, the columns of Q transpose itself is row of again the same some other row.
Some other row only. So
Not corresponding to
okay, you are right. Some other row, it consists of 0, 1, minus 1, zeros and so on. Okay. So we claim that this will be minus 1 if the indices I is adjacent to j. Okay, that is the edge starts at I, ends at j, or the edge starts at j and ends at I. Okay, these are the only two possibilities. So either here you will get a 1 here, corresponding to that 1 you will get a minus 1 here, or you will get a minus 1 here, corresponding to that you will get a plus 1 there. Okay, if there is no edge between them, then it will be 0. Okay, what is the advantage of having this type of representation, this formula? Positive semi-definite. The moment you are writing a matrix as a product of two matrices of this form, B transpose something like this, then you get it's a positive semi-definite matrix. Okay, so that is one observation. This Laplacian is a positive semi-definite matrix. So this is a symmetric matrix, symmetric and positive semi-definite. So all the eigenvalues I can arrange in this way. So lambda 1 less than or equal to lambda 2 or equal to lambda n. These are the eigenvalues of the Laplacian. Okay. Something more can be said about this L of G. What are the row sums of this matrix L of G? The row sum of the matrix L of G is 0, because if you take all ones vector again, L of G into E, this will be 0 into all ones vector. So 0 is always an eigenvalue corresponding to the eigenvector all ones vector. Okay, so 0 is always an eigenvalue irrespective of the graph. Okay, now the second smallest eigenvalue, this lambda 2, will tell you whether your graph is connected or not. Okay, so that we have already seen that. What is rank of L of G? Rank of L of G is rank of Q of G transpose into Q of G. So one of the fundamental theorem in linear algebra, rank of A transpose A is same as rank of A. So if lambda 2 equal to 0, then rank of L of G is at most n minus 2. That means that rank of Q of G is at most n minus 2. That means that this graph G should be a disconnected graph. Okay. So if lambda 2 is equal to 0, then the graph G is disconnected. If in fact if and only if G is disconnected and if the graph is disconnected, if G is disconnected, again a similar type of argument will tell you, then lambda 2 is equal to 0. Okay, so lambda 2 is an eigenvalue. This is an algebraic property or algebraic number associated with the matrix. Okay, so this tells you whether your graph is connected or not. Okay, so for this reason, Fiedler called this second smallest eigenvalue of the Laplacian as algebraic connectivity. So it measures or it tells whether your graph is connected or not. So by looking at the second smallest eigenvalue of the Laplacian, okay. So in fact, many more things can be said, like we can get a robust measure of the connectivity of the graph using lambda 2, something called Cheeger's constant. For the Cheeger's constant, it can give bounds for the Cheeger's constant using lambda 2, okay, both upper and lower bounds. Yes.
Using the same arguments, can you say number of components of G is multiplicity of 0 minus 1?
Number of components is multiplicity of
0 and then minus 1.
I think that should be true. So let me check. So in the connected case, what are you getting? So if the multiplicity of 0 is 1, then it has one component. The multiplicity of 0 is 2, then you will get two components. Multiplicity will tell you exactly how many components are there.
Yeah, that's what I want.
Without that minus 1.
Yes.
Okay, yeah. Okay. And I want to show you one of the important representation of this quadratic form associated with the Laplacian. Okay. So if I take any vector x in Rn, then this x transpose Lx, if you look at the quadratic form associated with this Laplacian, so this has a nice representation. So this can be written as sum of squares in this way. Okay, just take the difference of the entries of the vector which you are choosing. Okay, the difference is taken along the edges and square it. Okay, so many of the applications, if you see wherever the Laplacian matrices are applied, most of the cases I have seen this expression is used. Okay, so today I will show you at least two applications of this type of expression. Okay, so let us give a proof of it. So for Laplacian we have a formula in terms of Q of G, just apply that. This is Q of G into Q of G transpose X. So what is X transpose Q of G? It's a vector. What are the entries of this vector? X transpose Q of G, this is a row vector. What are the entries? The first entry is, you take the difference of the vector X, the entries of the vector X, okay, with respect to the edge, first edge. Okay, if ij is the first edge, then in the first component you will get something like xi minus xj and so on, corresponding to every place. Okay, next we are taking the transpose of it, it is xi minus xj and so on. So just take the dot product of it, you are going to get xi minus xj the whole square. I just explained for the first row. It's okay, right? You okay with this? Okay. Now, we'll show that if the algebraic connectivity of the graph is high, then we'll show that the graph itself should be well connected. Okay, so by well connected, what we mean? So I think most of you know what is the definition of vertex connectivity. What is the definition of vertex connectivity? The minimum number of vertices you have to remove from the graph so that the resultant graph should be disconnected. If I start with a connected graph, okay, if it is not a connected graph, then the number of components after removing these vertices should increase. Okay, that's the definition of vertex connectivity. This algebraic connectivity gives a lower bound for the vertex connectivity. Okay, so let us define vertex connectivity. So this is the, I'll write down the minimum number of vertices needs to be removed from G. Okay, let us take a connected graph. you can define for disconnected graphs too, okay, such that removal of these vertices disconnects the graph, okay.
So for complete graph, we'll have a issue.
What are you going to define? That I will discuss. What is the
Trivial means no edge.
okay? So either disconnected graph or a single vertex. You want to say that or okay? So vertex connectivity of Kn is n minus 1. Okay. So examples. So it's denoted by alpha of G. Okay. So what is alpha of Kn? N minus 1. If I take like complete bipartite graph, minimum of oh okay, okay, K I will use kappa in Bande and Murthy, what's the notation used? Okay, that alpha, beta, alpha for vertex connectivity, beta for edge connectivity. Okay.
Kappa and kappa prime.
Oh, okay, kappa I will use. Okay. Then what about Cn? Cn is 2. Okay. Okay, and so on. So Fielder proved that in 1960s. So he showed that the second smallest eigenvalue of the Laplacian gives a bound for this this quantity. Okay, this vertex connectivity. Okay, so let me state that. So maybe I'll prove a lemma first before giving the main theorem. Okay, so let G be a graph. And S be a subset of, okay, then okay, define G minus S. How to define G minus S? So G minus S is the graph, is a subgraph obtained from G by deleting the vertices of S and the edges incident with S. Okay, you take a graph and you pick up a subset of vertices. Okay, by G minus S I mean remove all the vertices in S and then remove all the edges which are having n vertices in S. Okay, so we can compare the algebraic connectivity or the second smallest eigenvalue of these two graphs. Okay, so what's the connection? Then lambda 2 of G, okay, this should be less than or equal to, you look at the lambda 2 of G minus S, okay, plus the number of elements in S. Okay, by lambda 2 of G I mean lambda 2 of the Laplacian. Okay, you are dealing with only Laplacian eigenvalues. Lambda 2 of G is less than or equal to lambda 2 of G minus S plus the number of vertices in S. Okay, let me check the statement. Okay, that's it. Okay, the proof is a nice application of the sum of squares expression. Okay, we will do that. Okay, so maybe I will recall something about the variational characterizations. We can for lambda 2 you have a nice formula. This is minimum over let's take x transpose Lx to normalize it. Yeah, let me normalize it with the norm x is equal to 1. Okay, 2 norm equal to 1. Then it should be orthogonal to the eigenspace corresponding to the eigenvalue 1. Okay, so it should be orthogonal to then the all ones vector. Okay, the variational characterization you have seen, right? So lambda 2 is equal to minimum of, if you want to see a proof, maybe in the tutorial we can do that. Okay, so lambda 2 is given by this formula. Okay, okay, now let us start with let us take the vector, the eigenvector corresponding to the x. Okay, so let me start with the, let x be the eigenvector corresponding to the second smallest eigenvalue of g minus, okay, I'm using y there, I will stick to y. Okay. I'm assuming this is normalized, that is 2 norm is same as inner product y with y, y transpose y equal to 1, and y is orthogonal to all ones vector. Okay. Now I'm going to use this vector to construct a vector x in Rn. Okay, so maybe I didn't use any numbers for it, any dimension I didn't mention anywhere. Okay, so now you define, or maybe it's better to mention that this lives in y lives in r power cardinality of g minus s. Okay, that is n minus cardinality of s. I'm going to define a vector x in r power n as follows. Okay, we'll construct a vector x using y. So what's the natural way? I want to keep this orthogonality and norm 1. We can just append zeros. Okay, so this is the way I am defining xi to be equal to, you keep yi if I is in s, 0 otherwise. Okay, then the 2 norm of x is same as the 2 norm of the vector y, this is equal to 1, and the inner product of x, y and x with e is equal to 0. Okay, so I have a vector which is orthogonal to all ones vector and it has norm equal to 1, hence I can look at the variational characterization for the second smallest eigenvalue of g. Okay, so let us look at the second smallest eigenvalue of g. So lambda 2 of g is equal to minimum over some norm z is equal to 1, z is perpendicular to all ones vector in Rn, okay, into x transpose Lx. X transpose Lx is same as this we have already derived here. This is summation over I adjacent to j zi minus zj the whole square. So this quantity, so this x is a particular vector in this collection, so lambda 2 is less than or equal to summation I is adjacent to j xi minus xj the whole square. Okay, now what can you do? The part of this sum you can replace by this lambda 2 of g minus s, right? So we'll split the sum into two parts. So one part is corresponds to all the edges which are part of g minus s, and then whatever is left out. Okay, So maybe G minus S. Okay, let us give a notation for the edge set. Let E prime equal to the edge set of G minus S. Okay, so with this notation, this is same as the edge Ij belongs to E prime xi minus xj square plus summation belongs to E is the edge set of the graph G, E minus E prime xi minus xj square. Are we done? So this can be rewritten as in this way. This is same as, so this quantity is Ij in E prime, that means that both I and J are in G minus S. So this will be same as Y minus Y transpose Ly, that is same as lambda 2 of G minus S. Okay, so this quantity is same as lambda 2 of G minus S. The second term we can simplify in this way. So I belongs to S and summation I J E xi minus xj square. Then what about this quantity? I is in X, I is in S, J is in S complement. So if I is in S, then what is the value of Xi? Xi is Yi. What's the value of Xj? It is not in S, so that is 0. Just I will get Xi square. So this is equal to, maybe here I can put a less than or equal to. Okay, just I am considering only i's. Maybe some edges may be there, both the ends are inside S complement itself. Some of the edges can be there, both the ends are inside the S complement itself. So you can keep a less than or equal to here. That will not affect our work. Plus summation I belongs to S, summation.
So yes, Charlie, yes.
Sorry? Because of some of the edges which may have both the ends in S itself. Okay, so those things also we are discarding there. That's why we need a inequality here. Okay, so this is Yj square. Okay, but Yj square has length equal to 1. We are taking only part of that vector y. So this will be less than or equal to 1. Okay, so this sum is less than or equal to 1. So this is less than or equal to lambda 2 of G minus S plus summation I in S. Okay.
So here, I just have a quick question. So
Yes.
xi should be yi if I is not in S.
Sorry.
In the definition of xi, shouldn't be that y.
Yeah, you are right here. It should be in
Yeah.
G minus S.
Okay.
The complement. Yeah. Thanks. Yeah. So it belongs to S. So I'm writing here Yj square. Yeah, correct. Okay. This is same as lambda 2 of G minus S is lambda 2 of G is less than or equal to lambda 2 of G minus S plus the number of elements in S. Okay. Are we done? From here, can we conclude that the algebraic connectivity should be less than, the lambda 2 should be less than or equal to the vertex connectivity? So if we take a set S whose removal disconnects the graph, so G minus S is a disconnected graph. If G minus S is disconnected, then what do you know? Lambda 2 should be equal to 0. Lambda 2 of G minus S is equal to 0. So if you substitute here, what you will get? Lambda 2 of G is less than or equal to lambda 2 of G minus S, that is 0, plus number of elements in S. S is the set whose removal disconnects your graph. So that shows that lambda 2 should be less than or equal to the vertex connectivity. Okay. So as a consequence of this, okay. So this says that lambda 2 of G is less than or equal to lambda 2 of G minus S. This thing. Okay. So as a consequence of this, if G is other than Kn, okay, complete graph on n vertices, then you have lambda 2 of G is less than or equal to the algebraic connectivity of G.
Interlacing property
You don't need interlacing here.
We are considering only integer subgraph whenever we are removing S from G. So that second smallest eigenvalue is always greater than or equal to the second smallest eigenvalue.
That's a good question. I think Sebi explained when he was doing. When you are considering a subgraph, and if you consider the Laplacian corresponding to the subgraph, that need not be a principal submatrix of the Laplacian of the original graph which you started. Degree may vary. Interlacing we can't apply in this state. Okay. Okay. Yes. When does equality holds? Do you have any characterization for equality?
I think you can calculate here. So when you go from when you have a little bit up, when you have the inequality, yeah. So if you see like in the sum above it, like where you put the 1, you can make it a little bit more precise because so what you get for every so that one is, I think it should be J should be not in S, because so the
okay.
yeah so something about the J not in S. So when you do the calculation there, you basically, it's going to be lambda 2 of G minus S is clear, and then you're going to sum up for every J not in S, you will sum up Yj square as many times as you have an edge from that J, an edge that goes into S, and that's going to be the degree of the number of neighbors of J intersect with S. So you write it like that, like a summation for all over J not in S of that, and then you can upper bound it by cardinality of S. So you can analyze. I think equality happens here. You have to have like some kind of all the edges in between or something like that.
Okay, S is an independent set setup. Yes, you need to be independent set or?
I don't know if S has to be independent because S is kind of. My impression is that you just need all the edges between S and G minus S.
Okay.
Yeah,
S may have some edges, but
yeah.
I don't know. Maybe we can discuss that in the tutorials. Okay, we'll see. Oh, join of two graphs.
Yeah, so that's
okay,
exactly what it means. The S and everything else, you have all the edges between S and G minus S.
Okay,
That's
okay.
the same as a join.
Is it the paper by Steve and Pati? Kirtland and Pati? Okay. I think there is a paper about it.
Yeah.
Steve Kirtland and Sukanta, they wrote. Yeah, correct. Okay. So do you have any doubt on this part? I'm sorry about these notations. Yeah, this should be. So we are rewriting the edges which are not part of E prime, which are in E. Okay. So here when I write less than or equal to, I'm going to skip some of the edges. So for that I wrote the inequality here, but here I should have mentioned J should not be in S. Okay, that's okay. So this idea is very common, like so you just cleverly construct some vector and put it inside the quadratic form. Okay, that will help you in lot of other instances. So I will tell you two more things. What else I have? Okay, so define something called bisection problem. The problem here is you have to partition the vertex set into two parts subject to some constraints. Okay, so our setup is G is a simple graph, then if you give a partition, if it is given a vertex set by partition, say V equal to V1 union V2. So define the boundary, or denoted by this dou of V1 comma V2 is the set of all edges, okay, which are having Vi comma Vj such that Vi is in V1, Vj is in V2. Okay, so you have a graph G, you have V1 something like this, V2 something like this. You collect all the edges between the partition V1 and V2. Okay, so even though we write here bipartition, like it's not really a bipartition, like between the vertices of V1 you may have some edges. Okay, just we want to partition the vertex set into two parts such that partition the vertex set into two parts and then collect all the edges which are passing from V1 to V2. Okay, so this is also called a cut. This is a cut. If you take for some V1 subset of V, V1 V minus V1, this is called a cut. Okay, here we don't know, like V1 and V2 they may overlap. Okay, there may be some overlapping. So here if you consider V1 and the complement of V1, then we are going to call this this is cut associated with that vertex at V1. Okay, so bisection. So this is the definition of bisection. It's a bipartition of the vertex set of its vertex set. Okay, in which the number of vertices in the partition V1 and V2 they differ by 1 at most. Okay, in which number of vertices in the two parts are differ by at most 1. So if number of elements in V, if number of elements in V is a even number, then it's like you can equally partition V1 and V2 V1 and V2 to have same number of elements. Suppose number of elements in V is odd, then we can't expect for a equal partition. So at most one difference is allowed. Okay. The problem is just only for even cardinality I will define. Let cardinality of V be even. Define B of G. Okay. This is called the smallest bisection. Okay. The smallest bisection of G. Okay. As follows. B of G is equal to minimum over all subsets of V with cardinality of S is equal to cardinality of V minus S. Okay, just to minimize the number of edges between the set S to its complement. So definition clear, the smallest bisection of G denoted by B of G, that is given in this way. So you take a cut, okay, such that the vertex set associated with the cut has the property that number of elements in the set S is equal to the number of elements in its complement. Okay, so I'm assuming cardinality of V is even. You have to minimize this quantity. Okay, so you have to find out this number B of G. It's a problem. Huh?
In the definition of bisection, are the two parts allowed to intersect or not?
So S and V minus S.
Here no, but
So here it is, when I'm defining this one, they can overlap, but here after this I'm not allowing to overlap.
here, when this is just the smallest edge content.
No, but the parts are equal.
Constraint is the cardinality of S is equal to cardinality of V minus S.
So you want to split the vertices in half.
Yeah.
So if you don't have that restriction, this would be edge connectivity.
What's the complexity for edge connectivity? Computational complexity. Calculating that quantity.
I think it can be done efficiently.
Efficiently, polynomial time. Okay. Okay. Then this problem is more interesting. When you put one more constraint, this is an NP-hard problem. You don't have any easy algorithm to solve this problem. You will see a spectral bound for this quantity B of G. Okay. So you have to calculate this B of G. Okay. So this is one of the hard problems in computation. Okay, so we don't have any efficient algorithm to calculate this quantity B of G for all families of graphs. Okay, so this is a useful technique. Suppose if you can't calculate some quantity efficiently, then you go for some relaxation. Okay, or try to establish some bounds for it. Okay, so morning I think SEBI did one thing, the independence number. I think that's also NP-hard quantity to calculate. Okay, you can think of that's a bound for these things. Okay, and there is an interesting reason follow up for what SEBI did in the morning, that the bounds are not tight. Okay, they're far away from tight. So there is a paper which title itself, this inertia bounds are far away from tight. Okay, I think 2019 or 2020 it appeared in Journal of Algebraic Combinatorics. If you're interested, you can see that. Okay, so here like we are going to establish a spectral bound for this quantity B of G. Okay. Okay, so I am going to again do a trick. This is well known and useful in found in many of the applications. Okay, so given a cut or given this set S, let us associate a vector with it. Okay, a vector of size n. Okay, assume that the cardinality of V is n. So if you give a subset and then what is the natural vector one can define? The characteristic vector you can see. Okay, with the +1 and -1. So let us define that vector, and that gives us something interesting. Okay. So let me take, since we are taking minimum over a finite collection, this should be attained. Let us take S1 be the subset for which this minimum is attained. Okay, let us start with that. Let S1 be the, or S1 be a optimal bisection. Okay, so S1 be a an optimal bisection. Then corresponding to this S1, define your vector. Define the vector x in Rn as follows. This is like the characteristic vector. Xi, define it to be equal to 1 if I is in S, and define it to be minus 1 if I is not in S. Sorry? Okay, I'm yet to state it. Yeah, correct. Then okay, so then what is x transpose x for this vector? What is x transpose x? No, it's not 0. The n, okay, cardinality of the vertex set, that is n. And what is x transpose Lx? This is, we use the formula which we derived, okay, so that is xi minus xj the whole square. Now see the possibilities for xi minus xj. So xi and xj both are either, both of them are from the set plus minus 1, okay. So if xi and xj both of them are having same sign, then 0, okay. So in terms of the definition of the vector, you see, if xi and xj, if both of them are same sign, then both of them should be either in S or both of them should be in the S complement, okay. So this will be different from 0 only when xi is in S and I is in S and j is in S complement, or vice versa, okay. So that's going to give me 2 square, that is 4, it's the same as 4 times the number of crossing edges, that is same as So with this observation, I can state the theorem. So theorem says that B of G, this quantity, is greater than or equal to n over 4 times lambda 2 of G. Okay, this lambda 2 of G is the second smallest eigenvalue of the Laplacian. What's the proof? So again, look at this formula. Lambda n is equal to minimum over that quantity. Okay, and maybe one more observation I can make here. So sum of the entries of this vector xi, that is 0, because cardinality of S is equal to cardinality of V minus S. So that is same as saying that this vector x is orthogonal to all one's vector. Now you can see the vector which we constructed here, that satisfies all the constraints, except this is not having norm equal to 1. Maybe you can normalize it by 1 by root and something. Okay, so lambda 2 of G, you have the formula minimum over is equal to 1, or the other version I will use x different from 0 with x is perpendicular to E, x transpose Lx. This is same as the same minimum summation xi minus xj the whole square divided by x X transpose X. Okay, X I already used, we will use Z. So this is so the minimum, this should be less than or equal to what's the result? So this should be less than or equal to, if I replace the minimum the collection by a particular vector X which satisfies this condition, then I'm going to get this is less than or equal to the numerator. Okay, I will write one more step. This is less than or equal to I adjacent to j xi minus xj whole square divided by X transpose X. So now you get the result. That is lambda 2 of g is less than or equal to, the numerator is 4 into X transpose X is n, this is n. Okay. I have taken it to be S1. So this implies for the cut for the cut S1 the minimum is attained. So that is same as B of G is greater than or equal to 4 by n, that is n by 4 into lambda 2 of G. Okay. It's a nice idea, good to know when you are doing Laplacians. And one more result related to max cut. So how many of you know max cut? Max cut. Okay, I'll recall. It's a max cut problem. So this says that G equal to V comma E, this is given to you. The problem is find a subset S of V such that the cut associated with the this S is maximum. Here we don't have any restriction on S. Cardinality of S and S complement can be anything. It's a kind of problem similar to bipartition. You are bipartitioning the vertex set into two parts, but you are not restricting that. Cardinalities are the same, and that is a minimization problem. This is maximization problem. Okay. So the number max cut is denoted by MC of G. Okay. The max cut in a graph G is denoted by MC of G, is defined as follows. So MC of G is maximum of the cuts with just AC subset of V. Again, this is a hard problem to solve. Okay, you don't have any easy algorithm to calculate this quantity for given arbitrary graph. Okay, so we will give a bound for this quantity in terms of the largest eigenvalue of the Laplacian matrix. Okay, it's a result by Mohr and Polyak. I'll give a proof of it. The idea is same, just we are going to associate a characteristic vector and we'll use that vector to establish that spectral bond. Okay. Okay, so theorem and then I'll write the proof. I forgot to write, so theorem. The max cut of the graph G is less than or equal to n over 4 times the largest eigenvalue of your Laplacian. Okay. So again we are taking the maximum over subsets of V. It's a finite collection. The maximum will be attained for a set. Okay. So let us start with the set. Let S be the set for which the maximum is attained. Let S be a subset of V such that the maximum is attained, such that MC of G is equal to cardinality of S comma S complement. Okay. So now define a vector x in Rn as follows. Just a characteristic vector. Define xi to be 1 if I is in S, and define it to be -1 if I is not in S. Okay. So you know the variational characterization. What is the formula for lambda n? The largest eigenvalue of the Laplacian. For any symmetric matrix, what is the formula? Take the take the maximum. Okay. So maximum over y different from 0 in Rn. Y transpose Ly. Okay. So again I am going to replace this maximum by a particular vector. So I can put a greater than or equal to, this is x transpose Lgx by x transpose x. Okay. So that is same as, okay, I'll write one more step. This is Lgx divided by x transpose x. This quantity is, use the sum of squares expression, ij rise into j, xi minus xj the whole square divided by, what is the quantity? That is n, right? Now what is the numerator? Xi minus xj, 4 times the size of the cut. Okay, this is 4 times the size of the cut, that is MC of G. So this is one way to formulate a combinatorial problem into a spectral graph theoretic problem and solve. There are many more techniques. Even one of the well-known approximation algorithm to calculate MC of G is due to Gomans and Williamson, that uses some semi-definite programming. Okay, which I am not going to discuss. Okay, so the interesting thing is, I think that algorithm will give a solution. The correctness is up to 0.878. Okay, and this is established in 1990s. So far there is no improvement. I think if you can improve it, it's going to solve this GUS conjecture in something global, something is there. Okay, so I can give you a reference where you can there is a readable introduction to all those things. Okay, so in fact one of the authors, Gomans and Williamson, David P. Williamson, so he offered a course on spectral graph theory. In his webpage you can find his lecture notes. He explained those things really nicely. So most of these things I have taken from that lecture notes. Okay. So okay, maybe just we have some time, we'll just discuss something about Laplacian matrices. Okay, so let us consider the complete graph, okay, Kn. What are the Laplacian eigenvalues of the complete graph? So you know adjacency eigenvalues, okay? If Kn is the complete graph, what is the adjacency spectrum? A of Kn is -1 with the multiplicity n minus 1 and n minus 1 with the multiplicity 1, okay? And you know, maybe first course in linear algebra, you might have studied this result. If you have, if you know eigenvalues of a matrix, let's say B, if you know all the eigenvalues of your matrix B, suppose let's say lambda 1 to lambda n are the eigenvalues. Suppose if you want to calculate the eigenvalues of the matrix B plus AI, then what are the eigenvalues of this matrix? Lambda 1 plus A, lambda 2 plus A up to lambda n plus A. So if you use this result, you can get the Laplacian spectrum of Kn from adjacency spectrum of Kn. What is the connection here? L is given by D minus A, but D is n minus 1 times identity minus A, okay? So this result says that n minus 1 minus the adjacency spectrum. So this is going to give me n with the multiplicity n minus 1, 0 with the multiplicity 1. Okay. So one interesting thing is the like the spectrum. If the spectrum of a graph is Laplacian spectrum or adjacency spectrum, okay. If it is given in this n with the multiplicity n minus 1, 0 with the multiplicity 1, okay. If you have any graph which have spectrum as this quantity, this set, then that should be complete graph, okay. These type of graphs are called graphs determined by their spectrum, okay. And this proof is not hard. Can you give me some suggestion? The proof is really simple. Maybe first time if you are seeing, maybe you have to work a bit. Sum of the eigenvalues is yes. Yeah, you can properly say that. So his argument is, consider the Laplacian matrix, look at the diagonals. The diagonals gives you the degrees. Yes, you want to say something? That's for the eigen adjacency. Okay. Yeah, you can use that. You can prove via adjacency also. Okay. So his argument is, take the trace. Trace gives you the sum of the vertex degrees. The first theorem of graph theory says that is equal to twice m. Okay. And that is for the complete graph, you are going to get n into n minus 1 by 2. If you take any simple graph, if it has n into n minus 1 by 2 edges, then the graph should be a complete graph. Okay. So for complete graph, it is really simple. Okay, the proof is the complete. So this gives the proof of the fact that complete graphs are determined by their spectrum. Okay. Now one more question is, so we can show that, say, the Laplacian eigenvalues of any graph, if you take the largest Laplacian eigenvalue should be less than or equal to n. Okay. So one question is, when n will be part of the Laplacian spectrum? Okay. So this says that if n is occurring as an eigenvalue with the multiplicity n minus 1, then complete graph is the only possibility. The question is, suppose just n, I don't know about the multiplicity, with the multiplicity at least 1, n is part of the Laplacian spectrum. Okay. Then also we can say something about the graph. Okay. So that I will prove in the afternoon. Okay. That maybe in a tutorial way we can develop the proof. Okay. You need to know notion of join and other things. Okay. So problem clear? When n will be an eigenvalue of the Laplacian matrix. Okay. So we will discuss that thing in the afternoon. And maybe we have 5 more minutes. I'll try to give one more result. If time permits, maybe Sebi will prove the matrix tree theorem. Okay, so so that says that if you take the Laplacian matrix, okay, I'm going to prove a fact related to the matrix tree theorem. Okay, if you take the Laplacian matrix, suppose if you want to count the number of spanning trees in the graph, okay, then using the Laplacian matrix you can get a explicit formula for it. That's known as matrix tree theorem. So that says that you look at you pick any entry of the Laplacian arbitrarily. Okay, now look at the cofactor associated with that entry. Okay, or in other words, just close your eyes, pick any random entry, remove the row corresponding to the entry and column corresponding to the entry, calculate the determinant of that submatrix. Okay, in absolute value, that is going to give you the number of spanning trees in the graph. Okay, so that so that one fact used in that in that proof of that result was this one. I'll just give a proof of it. If you take any matrix X, if X is any matrix, a square matrix, okay, if X is any square matrix, with row sums and column sums are equal to 0. With row sums and column sums are equal to 0, then the determinant of any of the submatrices, okay, Xij, okay, this is the notation I'm using. The submatrix obtained by deleting the ith row and jth column. Okay, and the determinants of all these matrices Xij's are the same, no matter whatever entry you are picking. Okay, so this can be thought of as I pick the entry Xij, then remove the row corresponding to that entry, that is the ith row, and remove the column corresponding to the entry jth column. Okay, so if you have a matrix X whose row sums and column sums are equal to 0, then the determinant of this submatrices are independent of the submatrix you are choosing. Okay, so Laplacian matrix satisfies this condition. Both the row sums and column sums are the same. Okay, so the proof. So let us look at X 1, 2. Okay, how does it look like? This is your X. Okay, we will start with X 1, 1. So this is our X11. Let us compare X11 and X12. Okay. So what is the difference in X11 and X12? Huh? So X11 is the matrix we obtained by removing the first column and first row. Okay. And X12 is the matrix obtained from X by removing the first column, sorry, the second column and first row. So what is the difference between X1? But only the first columns are different. Okay. Now look at the matrix X12. What can you say about this column? X12. Okay. So rest of the entries are the same for both the matrices. Okay. Can you compare this column X11 with this X12? That's the question. Okay. But we have both the row sums and column sums are equal to 0. since the row sum is equal to 0, it implies that if you sum all the entries of this x12, the columns of x12, if you put it here, that should be negative of this column. Okay, because in x12 I am summing everything. Okay, if I add the first column to it, I am going to get 0 column, since the row sums are equal to 0. Hence, if I skip this first column, if I sum everything and if I put it in the first place, in the x12, then that should be negative of this column. Okay, as we saw that the difference between x11 and x12 is only in the first column they differ. Okay, so the way, how do you get x12 from x11? Just replace the first column of x12 by x11. So you are replacing the negative of a column, negative of the column. Okay, hence the determinant will multiply by -1. And of course I claim the cofactor only I am claiming. Oh, sorry. The determinant, the cofactors. What is right? -1 power cofactor is better, instead of giving or -1 power I plus j you can put. Into the determinant. Okay, this, they are the same, or that is the cofactors, the same for any ij. Okay, so this proof will be this result will be used in the proof of matrix tree theorem in one place. Okay, so I want to. Okay, in the afternoon we will see the proof of this thing with some more things. Okay, so I'll stop here. Any questions? Okay, then we'll go for lunch.